Recording in progress.
Okay. All right. Hopefully everybody can hear me. Okay. All right. So we are finishing up convection and internal flow. So let's go ahead and get started. So problem 12, we have a pharmaceutical that is sterilized by heating it up from 25 degrees Celsius to 75 degrees Celsius within a 12.75 or 12.7 millimeter tube. So let's see. Let's put what's given here. All right. So, well. So I have whatever product this is, but it's coming in at, actually I don't like that color. Let's put it in. So a T mean in 25 degrees Celsius. And let's see what else. Coming in with a velocity, mean velocity of 0.2 meters per second. You can assume that the flow enters the tube. Actually, let's cross this guy out because I think we're going to be okay to be able to show this. And actually, I see one or two people from this morning's lecture. I made a calculation error and I realized it when I got home. But anyway, to be continued. We'll see shortly. But yeah, and we've got properties that are given to us. So we've got a density, we've got a CP value, we've got, and this guy is a specifically kinematic viscosity, and the units here should be meters squared per second. And everything else looks okay. And that's a 0.8 watts per meter Kelvin. Okay. So we want to know and I'm going to cross this guy out actually. Let me cross this guy out. And you'll see why in a hot second. But, all right. So I got things coming in. And here's the tube. Length is 10 meters. The diameter, D, what was that again? 0.027 or 127 meters. And then we've got things are coming out. T mean out, coming out at 75 degrees Celsius. I think we've got everything. Okay. And the things that we want to find the required heat flux for the process. So that's this guy right here. And you'll see that they do say that it's a uniform heat flux. So we're going to use the appropriate equation for that guy. And then we want to find the surface temperature. So T of the surface at X equals L. Okay. And then we'll kind of come back to why I crossed out part C in just a second. All right. I'm not sure if I need to assume anything, but let's see. All right. So it's a constant heat flux problem, and so we need to go to our equation sheet and use the appropriate equation. So let's do that. So I'll scroll on down here to my internal flow stuff, hopefully. There we go. All right. So I'm looking at this guy right here. So constant heat flux. So I think this first one is probably going to be useful to me. So I'm going to go ahead and write that down and see what else I can do. All right, so I've got Q double prime is equal to H at some x equals L times my TS at x equals L. I'll just put an L instead of x equals L minus, and I'm going to apply that heat flux. You know, it's applied uniformly along the length, and I'm going to apply it at a particular location, right at x equals L. So it's going to be the surface temperature minus the mean temperature at the outlet. All right. So let's see what I need to find. I think I've got the mean outlet temperature. I don't have the surface temperature. In fact, it looks like both of these have something that will, something involving A and B. So I need another equation. I've got two unknowns and one equation. So the other thing that I can do is, well, let's apply our first law. So this is our first law, and we're going to apply it to the fluid that's flowing through this control volume from x equals 0 to x equals L. So I have dE dt, and this is equal to Q dot minus W dot. I'm going to go ahead and put this in terms of Q, lowercase q, like we use in class. So it'll be little q minus W dot plus the sum of things coming in. So I have enthalpy plus kinetic energy plus potential energy all coming in minus the same thing going out. All right, perfect. And I'm going to go ahead and ignore kinetic and potential energy changes from the inlet to the outlet. So that'll go up here in my assumptions. The other thing that will go away is this dE dt, and then I'm also going to ignore W dot because within this control volume I don't have any power generated or required. So now I have Q, and I think my head's in the way now, so let me move that out of the way. I have Q is equal to m dot times delta H, which I'm going to put as m dot Cp delta T. And that delta T is from the inlet to the outlet. So it's going to be Q dot, and it's m dot, which I don't actually know, but I have enough information to calculate because I have that mean temperature coming in, or the mean velocity coming in. So that m dot is just going to be rho times my velocity times my cross-sectional area times my Cp times the delta T from the inlet to the outlet. So it'll be T mean outlet minus T mean inlet. Perfect. And let's see, see if I've got those things. So I've got a Cp value. It's in kilojoules per kilogram K, so I want to put that in joules per kilogram K. I've got a density, so I think I've got everything kind of that I need here for the most part. Yeah, I think we're good. And that's not a Q dot, it's just a Q. Yeah, let me fix that. There we go. Not a Q dot, just a Q. All right, so then this is going to be 1,000 kilograms per meter cubed times our mean velocity, 0.2 meters per second, times our cross-sectional area, which is pi d squared over 4. So pi times our diameter, 0.0127, and this is meters squared over 4. Perfect. So there's a cross-sectional area, then I've got a CP value. So not 4, but 4,000 joules per kilogram K. Perfect. And then it'll be my mean outlet temperature minus my mean inlet temperature. So 75 minus 25, which would be 50 degrees Celsius. A 50 degree Celsius temperature change is the same as a 50 Kelvin temperature change. So I'll put it in Kelvin just so it's obvious how the units are going to work out. And I get a value of 5060 watts. And I know that this Q double prime, that's related to that 5060 watts because, well, I know Q double prime is going to be Q over that surface area. So it's going to be the 5060 watts divided by pi dl. So pi times 0.0127 meters times our length, 10 meters. Perfect. So I've got a Q double prime, rewrite that so I can box it, of 12,682, and it's watts per meter squared. So I'll put a happy little bubble around there. There we go. Happy little cloud. All right. So I've got this guy. That's that one. And now it looks like if I wanted to find, I've at least got that. So that's part B, or part A, I mean. But I need, for part B, I need the surface temperature at X equals L. So this is going to be Q double prime divided by my local heat transfer coefficient at X equals L, plus my T mean outlet temperature. And somewhere I'm going to get an answer. So I'm going to preemptively put a happy cloud around there. But yeah, I definitely am going to need to find out what that H value is. So yeah, need that guy. All right, so let's go get him. So I need to find that local heat transfer coefficient at X equals L. So number one, is it laminar or turbulent? Okay. So, well, gotta calculate my Reynolds number. So my Reynolds number is going to be the mean velocity times our diameter over our kinematic viscosity. So I believe I have kinematic viscosity. I do. There we go. 2 times 10 to the negative 6. So it's going to be 0.2 meters per second. And then I've got my diameter, 0.0127 meters. And then I've got my 2 times negative 10 to the negative 6 meters squared per second. And I should get a value of 1270. All right, so my cutoff for laminar flow is 2300 for internal flow. So this is definitely laminar. All right, so that's good. It's going to help you pick the right coefficient, the right Nusselt number, local Nusselt number. So I've got that one. I also need to figure out, is it fully developed or not? Okay. So, yeah, if it's fully, let's see if it's fully developed hydrodynamically. So basically what we're doing is we're calculating where does this transition to fully developed flow occur, and then we're going to look at compare that to the length, right? Because that length is where we're evaluating that H value. All right, so for laminar flow, that critical, or that transition to fully developed hydrodynamically fully developed flow occurs at 0.05 times our Reynolds number times our diameter. So yeah, let's calculate that guy. This guy is 0.806 meters. So if you're listening from the lecture this morning, I need to put out a correction. I put 8.06, which changed things, because when we calculate, is it fully developed thermally, it's going to be this whole quantity right here, 0.05 times our Reynolds number times our diameter times our Prandtl number. And since our Prandtl number is 10, that's 8.06 meters. So comparing that to the length, we see that at 10 meters, it's already become fully developed, right? So hydrodynamically, it only, between 0 meters and 0.806 meters, it was developing, and from then on after, it was fully developed hydrodynamically. And then thermally, it was developing up until 8.06 meters, and then from then on out, it was fully developed. So there we go. So I would just say yes, yes. The Prandtl number, it was given to you in the problem statement. It's up there somewhere. Oh, sorry. There we go. It's right there. Okay.
So just to check, it's hydrodynamically up until 0.8 and then it goes thermally, or?
So it is developing, it's developing thermally. It's not fully developed thermally until it hits. So if this is 10 meters, it's about 8 meters before, like, all in this region right here, it's developing, and then from then on out, it's going to be fully developed thermally. We don't really care, because we're interested in, you know, over here at x equals L, right? So it's fully developed as far as we care, right? And any of those, in fact, let me pull up our equation sheet here. There we go. So any of these, if it's a local Nusselt number, as long as if you're calculating local Nusselt number, if it's in that fully developed region, then great. As far as the average Nusselt number, if I needed to calculate the average Nusselt number, even though there's a period or there's a region of a developing flow, that's okay. I mean, as long as like, you just have to look at the conditions for these empirical relationships to see when they would be applicable. So if it's fully developed, I don't know what I'm trying to say, but you just have to look at the conditions that those relationships are telling you. So for example, down here, it says it's fully developed. That takes into consideration that, yes, there was a region of developing flow. So they are separate evaluations. Yes, so if it says it is, It is, yeah. So these ones that the ones that say it's fully developed, they're saying it's fully developed both thermally and hydrodynamically. There are other ones that say like thermal entry or combined entry. What they're saying there is that it's something is still developing, either thermally, right, thermally, or combined. Maybe it's developed thermally but not hydrodynamically. All right. Okay. So with that being said, we have laminar, fully developed flow, and we have the condition of a constant surface heat flux. All right. So we're going to go over here. So that's this case right here. If you recall from the video that talked about these empirical relationships, there's no deriving those relationships, right? They're all empirically, experimentally put together, right? So you're not mathematically trying to derive that from energy balances or anything like that. So you just have to look at, here's the conditions that apply when I use them. So our Nusselt number is 4.36. All right. So I know that my local local heat transfer convection coefficient is going to be, all right, it's going to be my Nusselt number times my thermal conductivity of the fluid over my diameter. So the local Nusselt number is 4.36. Thermal conductivity of my fluid should be on, yeah, it's in my problem statement, so 0.8. Let me make this a little bit bigger. 0.8 watts per meter Kelvin. And then I've got a diameter here, 0.0127 meters. Perfect.
Where's the 4.36 coming from?
It's coming from our equation sheet.
Oh.
Yeah. Okay, sorry, my dog's going crazy. All right, so I've got 274.6, and it's watts per meter squared Kelvin. And so now I can plug that in way up at the top there. So let me highlight it, I guess. Now we know this guy, right? And so we can plug things in. And I've got a value of, this is 121 degrees Celsius. All right, so hopefully you got that. If you don't, I'm happy to go back, but in the meantime. Okay. All right, so now we have air coming into a thin-walled tube. We've got a diameter given to you and a length, 100 degrees Celsius. I think this must be our mass flow rate because it's in kilograms per second. We have properties, density we're given, we've got a CP value, we've got a viscosity. Again, this is the kinematic viscosity, and this is meters squared per second. We've got, that's a dividing. We've got a thermal conductivity in watts per meter Kelvin, and then we've got a Prandtl number. So we've got several things here. In fact, I'm going to add a line here, and I'm going to change this to C and D, because we're going to end up needing to calculate the mean temperature at the outlet anyhow. So this is the mean temperature at the outlet we're going to calculate. All right, so let me draw my picture. All right, so we have air. And it's coming in at a mean inlet temperature, 100 degrees Celsius. And I guess that's really all I need to say about that. Oh, and a mass flow rate. There we go, mass flow rate, 135 times 10 to the negative 6, and it is in kilograms per second. And then we've got our tube. Okay. And our tube is longer than what I'm going to draw here. So our length is 2 meters. And our diameter, let's see, diameter is 0.005, right? 5 millimeters, perfect. And then we are given the mean outlet temperature. So our mean outlet temperature, and it's given right here in part A, is 160 degrees Celsius. And something that is missing from this problem statement is that the heat flux is constant. Okay, perfect. Alrighty. So let's go ahead and draw some little arrows indicating that we have a uniform heat flux all along here. So a little Q double prime there. All right. I don't really know what I need to assume. Sometimes you don't know until you got it going. So I'll put this here and then we'll see. All right. So the first thing that I'm going to do is since I have to find, this first part A is asking for me to find the heat energy rate. So what they're asking for is just Q. That's what they're looking for. So for A, I'm going to find Q. And I know that Q is related to the heat flux, so let's at least start there. So actually, let's put him in red. Why not? So it's going to be our surface heat flux times the surface that it's acting through. So pi dl. All right. And then if I look at my equation sheet, same one that I had before, or same area that I was looking before. So these guys over here, constant heat flux. And it looks like I have an equation right here that will be useful. So let's go ahead and write that. So so my Q double prime, you can put a subscript S if you want to, but I'm just going to leave it off. Doesn't really matter. It's obvious that it's acting on the surface, but this is going to be H at some particular location. And I'm going to choose the outlet. So this is HL. Times T at the temperature of the surface at the outlet minus T mean at the outlet. All right. So I'm going to need to find the mean temperature at the outlet, obviously. But yeah, let's kind of divide it up. So the first thing I want to do is figure out, is the flow, is it fully developed at L equals 2 meters, right? Because that's gonna, is it fully developed, and is the flow laminar or turbulent? That's actually the first thing I need to write. So first thing is laminar or turbulent. Why are we having to find Tm out? They don't give us that. I'm sorry, did I say mean out? I meant the surface. I'm going to need this one. I'm sorry if I said mean out. I need the surface temperature at the outlet at x equals L. Yeah. In fact, I'm going to rewrite that. I'm going to put this as the surface at x equals L. All right, so I do need to figure out, is it laminar or turbulent? So let's calculate our Reynolds number. So this is going to be our U mean, times our diameter over our kinematic viscosity. And let's see, what did they give us? So they gave us, they gave us that. They did not give us, they gave us the mass flow rate, which is going to be definitely something that we're going to have to calculate. So I know m dot, it's rho times the mean velocity times our cross-sectional area, which is going to be pi d squared over 4. So my mean velocity, I'm sorry, my head's in the way. The mean velocity is going to be 4 times m dot over rho pi d squared. All right, so I can plug some stuff in here. So this is going to be 4 m dot d over rho pi d squared. Clearly one of those is going to go away. And then I've got my viscosity term here. Yeah, so kind of get rid of one of those at least, simplify it a bit. Do I have the density? I do. I've got that viscosity term, I got the diameter, I got everything I need. So this one is just really plug and chug. I ended up getting a value of 1494. And so that just tells me that it's laminar. Okay. And so that's going to dictate which relationships that I use over here. So let's see if it's fully developed hydrodynamically. So this is 0.05 times our Reynolds number times our diameter. I've got my Reynolds number now, so I just need to plug things in. I end up getting a value of, 0.37. Yeah, 0.37 meters. So, yes. So it's fully developed hydrodynamically. Let's see if it's fully developed thermally. So it's that same value, 0.05 times our Reynolds number, times our diameter, times our Prandtl number. If the flow, by the way, if the flow were turbulent, that position at which the flow transitions to fully developed, it would be the same for hydrodynamic and thermal. It would just be 10 diameters, and that's on your equation sheet. But anyway, so our Prandtl number is, this was air, so it should be 0.69. Yeah. So this one ends up being 0.26 meters. We're at 2 meters. So yes, it's fully developed at L equals 2 meters. So, okay, so we have fully developed laminar flow, and we have a constant surface heat flux. Okay, so let's look at our equation sheet. see what we got. See what would be useful for us. We need a Nusselt number is what we need. And yay, it's this one again. It's the 4.36 number. Actually, right? Yes, yes. So laminar, fully developed, uniform heat flux. So yeah, easy peasy, sort of easy peasy. So let me get rid of this guy. So I know that this local, local convective heat transfer coefficient is just going to be my Nusselt number times my thermal conductivity divided by my diameter. So this guy is 4.36, I think. Yeah, 4.36, yeah. So 4.36 times our K value, which is 0.0338, and it's watts per meter Kelvin. And then this is all divided by the diameter. Diameter was 0.005 meters. All right, so I end up getting a value of 29.47 watts per meter squared Kelvin. Okay, so perfect. Let's go ahead and at least write this with stuff that we know. So now I know the H value. That's my 29.47 watts per meter squared Kelvin. Put that in a box there. We need our surface temperature at X equals L, which I don't know. I do know the mean temperature of that fluid coming out, which is 160 degrees. Okay. So I still have two unknowns and one equation. Oops. So I need another equation as the upshot. Okay. So I'm going to go back to my equation sheet and see what would be useful here. So I think here, maybe, no, actually that's, because I don't, oh boy, haha, you are absolutely right, Caitlin is right and was being very patient and was wondering why I could not read English and also why I couldn't read what I wrote. So let's look. So it says if the tube surface at the exit is 160 degrees. That did not say the mean temperature, did it? It did not. So, I don't know it. But that's okay. I don't know that. But I do know the surface temperature at X equals L. She was so patient. Luckily, it's not that bad. We don't really have to erase anything except this guy down here. Because oops, now it's this guy. I don't know. So I'm going to kind of make sure that everybody can at least see the thing that I need to correct here. All right, so it's the surface TS at X equals L. So this guy is 160 degrees minus T mean at the outlet. Attention to detail apparently is my ability to do that. It goes down throughout the day. Okay. Now I can go back to my equation sheet because that will be helpful to me now. Y at the outlet. So you're, hold on a minute. Too many windows. All right, so why? There we go. So why at the outlet? Isn't it the rate entering? So we are defining the heat flux at a particular cross section. We're defining that heat flux right here. And then we're relating that back to Q for the entire thing, for the heat transfer rate in general, for the entire control volume. So this rate, this right here is just Newton's law of cooling applied right here, right? So you're just like we did, like with a wall, right? Here's the surface temperature of the wall. Here's T infinity. Well, we don't have a T infinity, but we have a T mean of the outlet, right? We don't have, and then our surface temperature is the surface temperature at X equals L, right? So it's just Newton's law of cooling applied to a particular location. Okay, so let's go ahead and get another equation. All right, so I'm going to go back to the heat transfer heat transfer packet. Yep. And so I'm going to use the second equation that I've got there. So yeah, there we go. Kind of clean that up a little bit. So it's going to be, I'm going to rewrite that guy. So I know that my T in out, and actually get this so I can see it. So my Tm out, which is the thing I'm trying to calculate. So it's T at a particular location. So on your equation sheet it says Tm out with a little, it's just reminding you that we're talking about a particular location X, and that's equal to that Q double prime, which we don't know, but we're going to calculate, times our perimeter over m dot times Cp, and then we've got a length here as well, plus Tmi. All right, and I actually know a lot of these things, right? This is going to be equal to, well, I don't know the Q double prime, but it's okay, I'm getting there. Times the perimeter. So the perimeter is pi d, and then we've got the length. Okay. I know those things. I know m dot because that was given to me, maybe. I think it was. Yes, that was given to me. And then my CP was also given to me. And then I also know this TMI. So if I were kind of going through and like thinking about what I know this guy, I know this guy, I know this guy, I know this guy, I know this guy. Basically, I know everything in there except those two equations. So now I have another equation right here, right? But now, instead of having two unknowns and one equation, now I've got two unknowns and two equations. And so it's up to you. You can solve. I just solved by substitution. Right, plug one thing in the other into the other. It doesn't really lend itself too well to elimination, but however you want to do it. So, but I end up getting surface heat flux. Surface heat flux of 227.86, and that's watts per meter squared. That wasn't what I needed, but I'm going to use that to calculate Q. And then I also got the mean temperature at the outlet. Can we do the same thing by applying the first law? So To find Q? Yeah, I think you could, because you know, so the question was, could you find Q by saying m dot, well, you'd still need, well, yeah, you would. Yeah, you would still be left with two unknowns. So yeah, the question was, can you apply the first law? So your first law would give you Q is equal to m dot C or CP times T m out minus T m in. You know this guy, you don't know the T mean out, you know this guy, you know this guy. So you'd have to get this. So you'd still be left with two equations and two unknowns because you'd need to get that surface heat flux. So yeah, I'm just gonna. All right. So I ended up calculating mean outlet temperature of 152.3 degrees Celsius. So I'm gonna box. Actually, I don't want to box it. I want to put happy clouds. All right, so this was B. Yeah, this is what we're calling B. And then A, remember we said Q is just going to be that surface heat flux times our surface area, which is pi dl. And now we know everything, right? We know our Q double prime, we know D, we know L. And so I end up getting a value of 7.15 watts. Perfect. All right. Perfect. So part C and part D, they're asking, so it says, and I'm going to scroll, Michelle. Make it so you can at least kind of see what it is. So it says, if the tube length were decreased to 0.2 meters, how would the heat transfer coefficient in part A be affected? So I'm not asking for a calculation. What I'm asking for is if the length were 0.2 meters, not 2 meters. How would our heat transfer coefficient, H, be affected? Would it be greater than, less than, or equal to the value that we calculated, which was that, where is it? Oops. 29.47. So let's see. 29.47. And it's watts per meter squared Kelvin. All right. So let's look at it. Let's kind of look at what that would affect. So the thing that would affect really is this part. Well, yeah, it's this guy. Both of these actually. So you can see that when we were calculating things before, we saw that, well, at x equals L, at x equals 2 meters, well, we're fully developed because it fully developed hydrodynamically at 0.37 meters, and it developed thermally at 0.26 meters. But if we've only got a length, if we've got a short cylinder with a length of only 0.2 meters, then it's not fully developed yet. So let's think about, well, what does that mean? Well, the flow would not be fully developed. So what does that mean for that heat transfer coefficient? So that local heat transfer coefficient. Remember, when we looked at our equation sheet, our Nusselt number that we used was a constant 4.36. And remember, if it's fully developed, if your flow is fully developed, if you recall, if I looked at the behavior of our H value, our local heat transfer coefficient, and we drew this before, I think yesterday maybe? I don't know, yesterday. The days sort of blend together. But it's going to be fully developed right there, and it's going to be some constant. But then before that, it's going to be like that. So, all right. So it wouldn't be fully developed, which means that it would be in that developing region. So our H value at 0.2 meters would be bigger than 29.47 watts per meter squared Kelvin, because this guy was calculated based upon we're fully developed. But if we're not fully developed, well, it's going to be in this region right here. Okay. And part D is asking if our MDOT, if it increases by 10 times. Same question. Is that local heat transfer coefficient that we used, 29.47 watts per meter squared Kelvin? Well, if the MDOT increases by 10 times, is that heat transfer coefficient going to be greater, less than, or equal to 29.47? So what effect does that have? And the effect that it's going to have is going to be on this, right? So you can see that the mass flow rate would increase, and that would increase that Reynolds number, and it would increase it by a factor of 10. So instead of a Reynolds number of 1494, you'd have 14,940, which would definitely be turbulent. So let's go back down here. So I'll just say that the flow, your Reynolds number, would be greater, a good bit greater than 2300, so it would be turbulent. And the effect of turbulence is to increase heat transfer, increase Q. So turbulence will increase Q by increasing that heat transfer coefficient. It's the same for flow over a flat plate. Turbulence is going to increase that heat transfer rate. It's going to increase that convective heat transfer coefficient. What was the original one? The original one was 1494. All right, so I'm going to give everybody just a hot chance to get that. All right. All right. All right, so let's work this last problem, and I may throw another problem on there just so you have an extra one. I don't know, in case you want it. But you don't need it. I'm just throwing it on there for extra practice, just let you know that if you want an extra one, you can have it. So problem 13. or 14, I'm sorry. So we have water flowing at 2 kilograms per second through a 40 millimeter diameter tube. So, and we're actually going to find two things, I think. No. Yeah, it's fine. So we have water. Got a mass flow rate of 2 kilograms per second. T mean in 25 degrees Celsius. And oops, so all this is going into the tube. Okay. And I don't know how long it is, but we'll see. So some length. Our diameter is 40 millimeters, so 0.04 meters. Perfect. And T mean outlet is 75 degrees. And of course I don't know what the length is, but yeah. There we go. That's one of the things that I'm going to need to find. So I want to find the length, and I think I also would like to find, let's find the heat transfer rate. I know it doesn't say it, but we're going to find it anyway because it's easy enough to find. And I will also go ahead and give you the properties, but I will make a note. You know, on a test, I've done it so far, probably going to give you the properties just so you're not wasting time, you know, looking those up. But your properties are going to be evaluated at what's called the bulk temperature. So evaluated at the bulk temperature, which is just the average of the inlet and outlet temperatures. So this would be, I'm actually going to write it. So T mean in plus T mean out divided by 2. So 50 degrees. Right, it's kind of like the film temperature for when we were talking about flow over a flat plate. It's the same kind of idea. You're just trying to get some sort of average temperature. Okay, so with that being said, we'll get a CP for water. We will get a dynamic viscosity. We'll get a thermal conductivity, and we'll get a Prandtl number. And hopefully amongst those things, we'll be able to get what we need, what we're looking for. So my CP is 4181, and it's joules per kilogram K. My dynamic viscosity is 547 times 10 to the negative 6 Newton second per meter squared. Thermal conductivity is 0.648, and that's going to be watts per meter Kelvin. And then my Prandtl number, 3.56. All right, perfect. So, and I think I need one more thing on my given that I didn't put, and that's that the surface temperature is a constant. And it's a constant 100 degrees Celsius. Perfect. All right. So, all right, let's calculate some stuff. All right, so I think I definitely need to go look at my equation sheet. So let's go look at that. There it is. Whoops, oops, 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 oops. All right, so we are not looking at this stuff. We are looking at this guy. So constant surface temperature. So I think, yeah, So it looks like this is going to be useful for getting Q, and of course I'm going to need to get this log mean temperature doohickey as well. Okay, so easy peasy. Maybe I'll get that one first because do I have everything? I do. I've got, yeah, I got my surface temperature. I got everything. So get my equation sheet so I have it there. All right, so write off your equation sheet exactly the way that it's written. Temperature is constant, surface temperature is constant. So I know that that Q is equal to, and it's going to be the average heat transfer coefficient times the surface area times my log mean temperature difference. And that log mean temperature difference is defined as, let's see. So I've got a delta T outlet minus delta T inlet over the natural log of the ratio of those two. So delta T outlet over delta T inlet. This is straight off of your equation sheet. All right. So this equation, in addition to the equations that we have for the constant surface heat flux, both of those were derived by doing energy balances on our control volume. So, all right, and then those delta T out, delta T in, those are defined as well. So this is our surface temperature minus T mean out. So in that case, well, our surface temperature is 100 degrees, our mean out temperature is 75, so that looks like 25 degrees Celsius. And then the inlet, I've got TS minus T mean in, so that's going to be 100 minus 75, 100 minus 25, which is going to give me 75 degrees Celsius. Okay, so I've got most of the stuff that I need, right? The surface area is just going to be pi dl. Great. I do need to find this guy though. All right. So, same questions, right? Is it laminar or turbulent? All right, so let's calculate that. So we got to figure out what our Reynolds number is. So our Reynolds number, mean velocity times our diameter. I've been writing it with our kinematic viscosity, but of course I've got things, the property here, yeah. So I need to write it in the correct terms. This is on your equation sheet as well. So rho times U mean times the diameter. Okay. All right. So, all right. And then I know I got the mass flow rate. I'm just going to kind of put a little thing here. So if I look at what I'm given here, I know what the mass flow rate is. So I do need to, I know m dot rho times U mean times my cross-sectional area, pi d squared over 4. So my mean velocity is just going to be 4 m dot over rho pi d squared. Okay, so let's plug that in there. All right. Oh, wait a minute. Did I do that right? Yes, I did. Okay. So I'll have rho times this guy right here. So it's going to be 4 m dot divided by rho pi d squared So clearly it doesn't, it doesn't even matter that it didn't have that density written down because it's going to cancel out. And then I've got a diameter here. I guess, really some of that's going to, like this will cancel out and one of that. And then I've got my viscosity down there, a dynamic viscosity. And I think that's it. And I know all of that stuff. So it really is, it's just plug and chug. I've got 1.16 times 10 to the 5th. So my critical Reynolds number it's greater than 2300, my critical Reynolds number, so it's turbulent. Perfect. All right. So normally here is where I would say, is the flow fully developed? I don't know. I don't know. I don't really have a good way of figuring that out because I don't know the length. That's what I'm trying to find. I don't know the length. But I do know that in turbulent flow, the flow develops very quickly. So I do know. But the flow is turbulent. And it'll develop very quickly. So I know that, thermally and hydrodynamically, it's going to develop at 10 diameters. So we're looking at, since our diameter is 40 millimeters, you'd be looking at 400 millimeters, 0.4 meters. So, as long as our distance, as long as that length is longer than that, then, we'll be okay. So what we'll need to do is we're just going to make the assumption, we're going to be calculating this stuff based on the assumption that it's fully developed. Otherwise, our analysis is going to get a lot more difficult. Okay. So, with that being said, okay. All right. So, for fully developed, turbulent flow, we need our H bar, and this, can you go back to the assumptions? Yes, I'm sorry. Yeah. We'll need our H bar, so this is going to be our average Nusselt number, times our thermal conductivity of the fluid, over our diameter. All right, and so I'm going to be looking for an equation for fully developed turbulent flow. So let's go look at our equation sheet and just see what fits the bill. All right, so basically we're going down the decision tree, right? What's going to be useful? So, all right, so I know, let's see. So I got turbulent flow, and it looks like, well, isn't that convenient? There's only one. Turbulent, fully developed flow, Prandtl number is in the right zone. Reynolds number, what was our Reynolds number? Yep, Reynolds number is in the right zone. I don't know about that L over D, because again, I don't know it. You'll notice that there's this little N subscript, or not subscript, but the superscript, so PR raised to some value N. That N depends on whether you're heating or cooling. So if you're heating because your surface temperature is greater than your mean temperature, which is what we've got here, right? The surface temperature is 100 degrees, and the mean temperature is going from 25 to 75 degrees. So when we, if this is the one, if this is the equation we're going to end up using, we're going to use N equals 0.4. On the other hand, if we were cooling, we would use 0.3. Now, one thing that might jump out at you is the fact that there's no bar over this. And this is something that I am actually going to put on your equation sheet, and I'm going to put it right here, and I'm going to do that after class tonight. for turbulent flow, and I'll put it right here. For turbulent flow, that average Nusselt number and the local Nusselt number are pretty much the same. Turbulent, fully developed flow. If it's not fully developed, there is a correlation in your book, but you're not going to need it for the exam. Okay. Okay. So I've got this, kind of ugly equation here, but that's okay. All right, so I'm going to copy that right off my equation sheet. All right, so 0.023 times our Reynolds number to the 4/5 times our Prandtl number. And it's raised to the value n, and since we're heating, we're going to use a value of 0.4. So there's that. And then we've got our Kf, thermal conductivity of our fluid over the diameter. So I got my Reynolds number, check. I've got my Prandtl number, presumably, do I? Let's see. Somewhere in here I've got it. 3.56. Perfect. All right, so I have enough information to calculate what this guy is. So I end up getting a value 6919. And this guy is watts per meter squared Kelvin. Perfect. All right. So I have some things, don't I? So let's I'm going to highlight the things that I have in this equation up here. So I know this, no, don't do that. I know this guy. Oops. I know this guy. Right, it's that guy. I know the surface area, because that surface area is just going to be pi times dl, right? And then I know my log mean temperature difference, right? I know that guy, right? Because I've got all the information over here to calculate it. But I do not have that Q. Okay. Well, and I can calculate it. I'm so stupid. I'm sorry. Oh my gosh, so stupid. So stupid. So stupid. I have everything I need to calculate it. Good gracious. Lord have mercy. What do I get? Something. 419. Lord have mercy. Hopefully you can still see this and kind of see it. Perfect. All right. I still don't have the length though. I need that. But I do have another equation on my equation sheet that might be helpful. So let's go there. Okay. So, yeah. Maybe this guy? Oops, that's ugly. There we go. That guy right there. He seems helpful to me. So I'm going to write that because he's got, you see there's an X in the E raised to all this stuff, there's an X in there. I'm going to use that. So let's close this out. So if this were part B to get A, we're going to use that equation on our equation sheet. I'm going to write it just like it is on the equation sheet. So I have Ts minus Tm at some location x over Ts minus Tmi, and this is equal to e to the negative. I've got the perimeter times x over m dot Cp H bar. All right, so my surface temperature, remember he's a constant 100 degrees Celsius. I am defining things at x equals L. So I'm going to define at x equals L. All right, because I need to find L. So the mean temperature of the fluid at x equals L is my 75 degrees. So 75 degrees Celsius. And then surface temperature, still 100 degrees Celsius. And then my mean inlet temperature is 25 degrees Celsius. And then, hold on just a second. Hello? Hey. Oh, I'm teaching a class. Everything okay? Okay. Okay. Fine. Sorry, that was my neighbor, and my kids are outside playing unsupervised, so I was just wanting to make sure that they were not in a ditch somewhere. Okay. So I have e to the negative. All right, so my perimeter is pi dl, which is what I'm trying to find. I'm sorry, pi d, and then times x, but at x equals L, divided by m dot, which I know, Cp, and then my h bar. Oh my goodness, all that raised. And remember, I already got a lot of these, right? There's my h bar. I've already solved for him. So it's just a matter of solving for L. So I have an L of 10.6 meters. Perfect. And it looks, looks like assuming that the flow was fully developed was probably a pretty safe assumption to make, because it looks like it only takes 0.4 meters to develop fully anyway. Okay. All right. I want to do one more. Okay. Let's do one more. I'm going to do one more. You don't need it, but we'll do one more just to give you one extra practice problem, because we do have the time, so why not? So I am going to scroll up to where I have some room, hopefully. Be nice to have like an extra piece of paper. I wonder if I can. Is that something? I might have broken it. Oh, okay. I'm using a different program because my other PDF annotator was awful. Getting really buggy. Okay, well, we'll do it right here. That's fine. All right, so get my problem statement over here. Here we go. So we have air at 200 degrees Celsius is heated. In a tube with a diameter of, oh, I may regret this, 1 inch. But we could put that in centimeters, can't we? So 1 inch, 2.54 centimeters. Let's do that. With a velocity, so a mean velocity of 10 meters per second. I know, I'm sorry. Okay, so we want to find the heat transfer. We want to find the, in fact, why am I not just, so I'll have this air, mean temperature at the inlet, 200 degrees Celsius, coming in with a mean velocity of 10 meters per second. And he's coming in. Okay, here's my tube. Bump it up. There's my diameter, 0.0254 meters. There we go. How long is this thing? Length, 3 meters. Okay. And we have a constant surface heat flux. So I don't know what that is. Suffice to say that it's constant. Okay. All right. And we want to know, we want to find the heat transfer per unit length. So Q over L. If we've got a constant heat flux and the wall temperature is 20 degrees higher, okay. So how do we want to put this? So the wall temperature is 20 degrees above the air temperature all along the length of the tube. Okay, so I'll say the mean outlet temperature is 20 degrees plus the surface temperature at X equals L. So it's 20 degrees all along the length of the tube. And so we want to find Q per unit length. So, okay, so here we go. All right, well, Q per unit length. So I'm going to apply Newton's law. Probably should capitalize his name. Newton's law, or Newton's law of cooling. And I don't know, let's apply it at X equals L. All right, so I have Q is equal to H at X equals L times, and it's going to be a surface heat flux actually. Surface heat flux times, and it'll be the surface temperature at X equals L minus the mean temperature at the outlet. And so what you can see is, well, it's just going to be 20, isn't it? TS, or minus 20, I guess, right? Oh, wait a minute, let's see. So if this is, I'm sorry, if the wall temperature, yeah. So the wall temperature is higher. The wall temperature is higher, I'm sorry. So this would be T surface at X equals L minus 20 degrees Celsius, because the wall temperature, the surface is higher, it's hotter than the fluid itself. Okay. So I'm going to write that. The wall temperature is 20 degrees. Yeah, you don't need it for the exam. It's just extra practice. Yeah. So 20 degrees above the mean temperature wherever, right, along the length of the pipe. right? So it's 20 degrees, the wall temperature is 20 degrees higher right here than the fluid is right there, and also at X equals L. There we go. And so now, that means that when we plug things in, I'll have, this becomes Ts at L minus the mean outlet temperature, so minus T of the surface at X equals L minus 20. So this is just times 20. All right. Okay. And then I'll also note, okay, well, Q is going to be equal to my surface heat flux times that area, so pi dL. So if I divided through by L, right, this guy and this guy goes away, so my Q over L is going to be my heat flux times pi d. So it's going to be HL pi d times 20 degrees. 20 degrees Celsius or 20 Kelvin, however you want to do it. So I just need to calculate this guy. So I'm going to do the same thing that I always do. First of all, figure out, is it laminar or is it turbulent? All right. So I've got to calculate my Reynolds number. There we go. So mean velocity times our, well, actually I'm going to give you, let's go ahead and give you some properties here. So our properties. So I'm going to give you a density. So 1.493 kilograms per meter cubed. I'll give you a dynamic viscosity, 2.57 times 10 to the negative 5. And this is kilogram, oops, not kilogram, meter, kilogram per meter second. Yeah, so I guess we got rid of those English units, didn't we? 0.0386 watts per meter Kelvin. Maybe I need a CP, I don't know, but we'll see. I got a CP is 1.025 kilojoules per kilogram K. All right, so yeah, so I guess maybe I need to put this in terms of rho, and then rho times my mean velocity times the diameter divided by my dynamic viscosity. And if I plug all those things in there, I get 14,756. So yeah, clearly turbulent. And for turbulent flow, if I wanted to know if it's fully developed, well, for turbulent flow, it's going to be fully developed at 10 diameters. And since our diameter is only 0.0254 meter, this is going to be 0.254 meter. So, yes, fully developed. Perfect. So let's go to our equation sheet and see what's going to help us, because I'm going to need, for turbulent, fully developed flow, I'm going to need, I have my local heat transfer coefficient, and I know that's related to the local Nusselt number, times that my thermal conductivity of the fluid over my diameter. So let's go to our equation sheet and we'll get a value here. So, oh, sorry about that. Go back. Come on. There we go. And it looks like, actually, I think this is going to help us again. So we have, oops, I'm sorry. We have turbulent flow. It's fully developed. Our Prandtl number is in the right spot. Yep, our L over D is greater than 10. Another way of saying it's fully developed. Reynolds number is 14,000. So yeah, I got that one too. And remember the previous problem, we used this for a constant surface temperature. This one's a constant heat flux, but it doesn't matter because we're still heating it. And so you stop that. You stop that. Don't be ugly. Don't be ugly. You're gonna be ugly, aren't you? You're gonna be ugly. You are. Well, okay. Well, that's fine. That's fine. I'll just close that guy because he's being... That's fine. Don't worry about it. Okay. I'll open it again. Whatever. It ain't gonna work. It's fine. It's gonna be annoying. But if you look at your equation sheet, still we're still heating that fluid, so the surface temperature is going to be higher than the mean temperature. In fact, it's going to be exactly 20 degrees higher all along the length of that pipe there. So perfect. So my Nusselt number is going to be 0.023 times our Reynolds number, which is the 14,000 number, to the 4/5 times our Prandtl number raised to the n is going to be n equals 0.4 because it's heating. I have a Prandtl number, right? Our Prandtl number is the... Do I have a Prandtl number? Probably. Yes, I do. I'll put him up here with the properties. My Prandtl number is 0.681. Perfect. So I got that. I got my thermal conductivity of my fluid. I've got the diameter. I have everything that I need. I end up getting 64.85, and it's watts per meter Kelvin. So perfect. I think I got everything. Got this guy, plug him in there, and so hopefully I've got enough information. I end up getting 103.5, and it's watts per meter. Perfect. So I'll kind of scroll out just a little bit in case you wanted to get a screenshot of that. All right. All right, so that's all I got. Like I said, I'm going to add another page of just conversion factors, just in case you feel like you need it. But so if you have questions, let me know. I'll turn on my 5-minute timer. But if you have questions, feel free to ask. I don't have office hours tomorrow, but my TAs do. But if you do have questions, just shoot me an email and I'll try to answer as well, okay? We didn't do problems 6 or 8. Oh, we didn't? Oh, no. Okay, well, I'll tell you what. Maybe we'll do it now. Yeah. I'm sorry, I did not realize that was not on there. So we didn't do 6 and we didn't do 8. Yeah. I tell you what, I will post a video of those. Yeah, I'll post a video of those, and that way you can have it available to you as well. Yeah, I'm very sorry. I did not realize that that was not on there. Yeah. So let me see. So let's see. So the flat plate subject to, I don't know, maybe we'll go ahead and do it. So yeah, we have a flat plate that's subjected to, if you want to hop off because you're like, but no, we were already done, that's fine. I'm going to go ahead and do it now and we'll just knock it out, okay? So, but if you want to hop off, my feelings are not going to be hurt, okay? But we have a flat plate subject to parallel flow. We got it on the top and the bottom. So here we go. So here's my flat plate. And I think, yeah, this one's got 6. So I'm gonna, if it's okay with you, if it's all the same to you, I am gonna go ahead. I'm gonna cross this guy out because it's the same. It's the same calculations, same darn calculations. It's just more of it. And I'm going to go ahead and I'm going to get rid of this guy right here. I'm going to cut the problem down a little bit. It's the same calculations. It's just more work, okay? So all we're going to do is we're going to look at a flat plate. We got parallel flow and we've got air flowing over this guy. So hits the plate. We have a boundary layer formation on the top and the bottom. So we have air, top and the bottom. So we have a U infinity, 5 meters per second. We have a free stream temperature of 20 degrees Celsius. And we want to find some things. So we want to find the average convection heat transfer coefficient. Okay, so H, so A. And then we want to find the convective heat transfer rate. So we're just looking for Q. And then we want to find the drag force. Okay. So, all right. So let's calculate some stuff here. All right. I'll throw my assumptions on there, and we'll see what we need to do. All right. So first things first, I'll go ahead and throw some properties here, out here. So at 50 degrees for air, yeah. So for air, at 50 degrees Celsius. Oh, I'm sorry. Air's not at 50. So we would evaluate these at the film temperature. So it's if your surface temperature is 50 degrees Celsius, then it would be the average of those. So 20 plus 50. So 50 plus our plus our 20 over 2. Yeah, so 35 degrees Celsius. All right, so our properties at that film temperature, I got a Prandtl number 0.706. I've got a thermal conductivity of my fluid of 0.0269. I have a kinematic viscosity of 1.669 times 10 to the 5th. I have, and that's meters squared per second, and then I've got a density of 1.135, and this is meter cube per kilogram. I'm sorry, I didn't even put any units on my, there we go, meters Kelvin. There we go. So there are my properties. So first thing that I need to do is probably calculate my Reynolds number and see if we're turbulent or laminar. So yeah. So for A, I know that this guy, this is going to be equal to my average Nusselt number times my length, times the thermal conductivity over my length. So I do need to figure out what my Nusselt number is. So, oops. All right. So first thing I'm going to do is I'm going to calculate my Reynolds number. All right, so my Reynolds number, let's see. So, let's see. So I've got my kinematic viscosity. So it's going to be, oops, I'm sorry. So it's going to be my U infinity times L. So this is going to be my Reynolds number at X equals L over my kinematic viscosity. So if I plug those numbers in, I've got everything. I end up getting 5.99 times 10 to the negative, times 10 to the 5th, not to the negative 5th. Okay. So we're pretty close. I need to figure out, and I know that, okay, well at X equals L, it's transition, it's already turbulent. However, I need to figure out, yeah, so at X equals L, the flow has transitioned to turbulent, which means that we have regions of laminar flow and turbulent flow, and so it's not my Nusselt number that I'm going to need to get is not just for turbulent flow. So I actually let me open up, see if this will open again. A second. There it is. You're going to be annoying to me, aren't you? I'm going to do this one then. Okay. So here we go. So this is page 5 of that PDF, that heat transfer packet. So it says at the very bottom, it says laminar conditions exist for the flow if it's laminar over the entire plate. So clearly we have transitioned into turbulence, and But then down here it says mixed conditions exist if flow began laminar but then transitioned to turbulence. If that transition to turbulence occurs pretty kind of close to the leading edge to x equals L, then you can approximate laminar flow. So I'll take this. So if this guy right here is greater than or equal to 0.95, basically what we're saying is that your transition to turbulence occurs really, really close to x equals L, so it's mostly laminar, so you could approximate it as laminar. So we can check that and see if we could use an equation for a Nusselt number for a laminar flow. It's worth checking. So your critical, this would be based on your Reynolds number equation. So it would be the Reynolds number, but the critical Reynolds number times that kinematic viscosity over U infinity. So this would be 5 times 10 to the 5th times our kinematic viscosity over our U infinity. And we have all those, right? So I end up getting, let's see, I end up getting 1.669. And so if I calculated that critical length over L, I end up getting 0.83. So I can't really say, well, it's mostly laminar, it's mixed flow or mixed conditions. Okay, so we have to consider that there is a region of turbulence or laminar flow and turbulence. So, okay, so let me pull up our equation sheet here. All right, so I need turbulent flow and I need an average. So it looks like, or not turbulent, but the mixed flow. So yeah, it looks like it's going to be this 0.0371 down here. So I don't know if you can, at the very bottom, the one, very, very bottom. Actually, I'll put it up at the top so you can see it kind of at the top. There we go. So it's the 0.037 times the Reynolds number to the 4/5 minus 871 times the Prandtl to the 1/3. So this is mixed conditions based on a critical Reynolds number of 5 times 10 to the 5th. Our Reynolds number was, I forget what it was already. It was almost 6 times 10 to the 6th. So it's less than 10 to the 8th. Our Prandtl number is within that range, so this looks good. So we're going to use this guy right here. So I know this is going to be my Nusselt number, so it's going to be, I'm going to put the KF out here, KF over L times my Nusselt number 0.037 times my Reynolds number to the 4/5 minus 871 times our Prandtl number to the 1/3. Perfect. So I've got my Reynolds number. It's this guy right here. I've got my Prandtl number, and so I just need to plug in and get an H value of 8.13, and this is going to be watts per meter squared Kelvin. So that's part A. All right. Oops. So that's A. Part B is asking for, what did it ask us for? Heat transfer rate. So that's Q. Okay, so we're looking over the plate. So, well, that's just going to be Newton's law of cooling, isn't it? So it's going to be the average heat transfer coefficient times that area, times my surface area, times the surface temperature minus T infinity. So surface temperature minus T infinity. And now we have that H bar. Our area, I think that was given to us. Yeah, it's 2 meters by 2 meters. But I do actually need to be kind of careful because the area that I'm looking at is going to be actually over the entire thing, right? So it's 2 meters by 2 meters, right? So my surface area is going to be on the top and the bottom. So 2 meters by 2 meters plus the other one. So really it's going to be 8 meters squared, right? So let's kind of make sure that's in there. All right, so I've got my H bar, I've got my area, I've got my surface temperature, it's 50, I've got my free stream temperature. So this one is plug and chug as well. So I've got 1950.7, and this is watts. Perfect. All right, and then we need our drag force. So let's look at our equation sheet and see if we have anything that will be useful to us. Yeah. All right. So you can see that that drag force is related to so your drag force FD, so it's up here at the top right hand corner, if you can see that. So top right hand corner, so it's related to, so it's FD over A is equal to the average shear stress over the plate. And then you can also relate that to the average friction coefficient. So that's what I'm going to do. So I'm going to write that exactly how it is on my equation sheet. But I'm going to move this out of the way first. Okay. There we go. Oops. So drag force. And it's drag force over area. Actually, I should write that too. Yeah. Drag force over area is equal to average friction coefficient times rho times U infinity squared over 2. All right. So this is going to be average friction coefficient times the area, which again is 8 meters squared, times rho. My rho is 1.135. This is kilograms per meter cubed. And then I've got a U infinity, which was 5 meters per second. This has got to be squared. And then I'm dividing all of this by 2. And I can get this for mixed conditions, right? Mixed flow, laminar and turbulent flow. So if we look on our equation sheet, let's go do that. And let's see what we've got. So, yeah, looks like equation 7.40 would be good, I think. So 7.40, and I'm going to write that exactly like we have on our equation sheet. So here we go. So our CF is equal to 0.074 times our Reynolds number to the negative 4/5 minus 1742 times the Reynolds number to the negative 1. So do I have a value for that? I don't. But I do have one for the drag force. So this one ends up being 0.257, and it is in newtons. All right. All right. I am not going to give you anything with radiation on this test. You'll have that next time. So this is it, okay? This is the only one. So don't worry about problem 8. This one is kind of fair game, I guess. So I'll leave that there in case you need to screenshot it. So on the test, so exam 4, 5 conceptual, like your homework, 1 external flow problem, and 1 internal flow. And that's it. So something with a pipe, something with a plate. There you go. All right, thank you. I'm sorry, guys. Sorry, I did not realize that I had skipped those problems. Sorry about that. All right, but hopefully you got lots and lots of practice. Y'all have a great night. I'm going to switch on my 5-minute timer. If you have questions, please feel free to ask, okay?
I'm sorry, say it just a little bit louder. You're real quiet.
Yeah, sorry, I didn't realize my mic was like on the floor.
Okay.
Let me see. The homework question was a multiple choice. Where did I put